Journey with me into the heart of an atom, a realm teeming with particles smaller than you can imagine. Here we encounter the photon, the fundamental particle of light. This tiny speck of energy, this quantum messenger, paints our world with color and illuminates the cosmos. But here's the strange part. The photon is a massless particle. It zips through the universe at the ultimate speed limit, untouched by the usual rules of mass. Imagine a feather, lighter than air, gliding effortlessly on the wind. That's the photon, a ghost in the cosmic machine. This concept of a massless particle might seem odd, almost magical, yet it lies at the heart of our understanding of light and the universe. It's a fundamental principle woven into the fabric of our reality. But what if we're wrong? What if this fundamental assumption is just a cosmic illusion, waiting to be shattered? Let's talk about speed. Speed is a fascinating concept that governs much of our daily lives. Not just any speed, but the fastest speed in the universe, the speed of light. It's the ultimate speed limit set by the cosmos. It's a mind-boggling 299,792,458 meters per second, or about 186,282 miles per second, a number so large it's hard to even fathom. Imagine traveling around the Earth 7.5 times in just 1 second. Einstein, the master of space and time, taught us something incredible about this cosmic speed limit. His insights revolutionized our understanding of the universe. In his theory of special relativity, he proclaimed that nothing, not even the most energetic cosmic ray, can travel faster than light. This was a groundbreaking revelation. Why? Because as something approaches the speed of light, its mass increases infinitely. This means it would require an infinite amount of energy to reach or exceed this speed. It would take an infinite amount of energy to push something to the speed of light, an impossible feat even in the vastness of the cosmos. This is a fundamental limit of our universe. This is the universe's way of keeping things in check. It's a natural boundary that ensures the stability of the cosmos. But remember our massless photon? This tiny particle of light is unique. It effortlessly cruises at the speed of light, unburdened by the constraints of mass. This allows it to travel at such an incredible speed. This is why light travels at such a breakneck speed. It's not bound by the same rules as everything else. Light is truly the cosmic speedster. Before Einstein revolutionized physics, a Scottish physicist named James Clerk Maxwell had already laid the groundwork for understanding light's speed. Maxwell's equations, a set of elegant mathematical formulas, described the behavior of electricity and magnetism. These equations predicted the existence of electromagnetic waves, ripples in the fabric of space and time that travel at a specific speed. When Maxwell calculated this speed, he got a remarkable result. It was exactly the speed of light. This was a profound discovery, revealing that light itself was an electromagnetic wave. And here's the kicker: Maxwell's equations, in their purest form, only work if light is massless. Add even a tiny bit of mass to the photon, and these equations, these pillars of classical physics, start to crumble. Now let's embark on a thought experiment. Let's imagine, just for a moment, that the photon isn't actually massless. What if instead it has a tiny, tiny mass, so small that we haven't been able to detect it yet? This simple what-if question, this tiny tweak to our understanding of the universe, sets off a chain reaction of mind-blowing consequences. It's like dropping a pebble into a pond and watching the ripples spread, changing the very fabric of the pond itself. The universe, as we know it, hinges on the delicate balance of fundamental constants and laws. A massive photon, however small, throws this balance into disarray. It's a tantalizing thought, a glimpse into a reality that might be stranger than we ever imagined. Section 5. A new speed of light, the cosmic ripple effect. If photons had mass, the first casualty would be the speed of light itself. Remember that incredible speed limit set by Einstein? Well, it might not be so constant after all. A massive photon wouldn't be able to reach the current speed of light. Instead, it would travel slightly slower. Its speed dependent on its energy. Higher energy photons would travel faster than lower energy ones, a far cry from the constant speed we know and love. Imagine the implications for astronomy. The light from distant stars and galaxies would take even longer to reach us, giving us a skewed view of the universe. The light we see from a single star would be a mixture of different speeds, creating a blurry, distorted image. Section 6. Gravity's pull on light, a dance of giants. One of the most profound implications of a massive photon involves gravity, the force that shapes the cosmos. Gravity is not just a force, it's the very fabric that holds the universe together. According to Einstein's theory of general relativity, gravity warps the fabric of space-time. This warping affects everything that moves through space-time, including light. And what travels through space-time? You guessed it, light. Light, which seems so constant and unchanging, is actually influenced by the gravitational fields it encounters. Even though photons are massless in our current understanding, their paths through the universe are bent by the gravity of massive objects like stars and galaxies. This bending of light is known as gravitational lensing. But if photons had mass, this gravitational interaction would be even stronger. The paths of these massive photons would be more dramatically curved by the gravitational fields they pass through. Light would be more susceptible to the pull of gravity, its path through the universe even more distorted. The journey of light would be like a river winding through a rugged landscape, constantly being redirected by the terrain. Imagine light bending like a river flowing around a mountain, its path sculpted by the unseen hand of gravity. This would create a universe where light's journey is a complex dance, influenced by every massive object it encounters. This would have profound consequences for our understanding of black holes, those cosmic monsters with gravitational pulls so strong that not even light can escape. The interaction between light and black holes would be even more dramatic. A massive photon might be slowed down enough to be trapped by a black hole, forever lost to the universe. This would change our understanding of the universe's most mysterious objects and the nature of light itself. Remember Maxwell's equations, the elegant formulas that describe the behavior of light? If photons had mass, we'd have to go back to the drawing board and rewrite these fundamental laws of physics. The massless nature of the photon is baked into these equations. It's a fundamental assumption that underpins our understanding of electricity, magnetism, and the electromagnetic spectrum. A massive photon throws a wrench into these equations, forcing us to rethink the very nature of light and electromagnetism. This wouldn't just be an academic exercise. Our entire technological civilization relies on our understanding of electromagnetism. From the electricity that powers our homes to the radio waves that carry our communications, we depend on these laws every day. A massive photon could revolutionize technology as we know it. Imagine harnessing the unique properties of massive photons to create new forms of energy, faster communication technologies, and even devices that manipulate gravity itself. The possibilities are both exciting and daunting. The implications of a massive photon extend far beyond our planet, reaching into the very fabric of the universe itself. They ripple through the vast expanse of the cosmos, impacting everything from the formation of stars to the fate of black holes. These ripples can influence the birth of new stars and the death of old ones. For example, the pressure of light plays a crucial role in the life cycle of stars. This pressure helps to balance the forces at play within a star, ensuring its stability over millions or even billions of years. It counteracts the inward pull of gravity, preventing stars from collapsing under their own weight. Without this delicate balance, stars might not shine as brightly or live as long, but if photons had mass, this pressure would be weaker, potentially altering the way stars form and evolve. The entire process of star formation could be different, leading to a universe that looks very unlike the one we know. Black holes, those enigmatic objects that warp the fabric of space-time, would also be affected. Their immense gravitational pull would interact differently with massive photons. Their gravitational pull would be even stronger on massive photons, potentially creating new and bizarre phenomena that we can only begin to imagine. These phenomena could include changes in the way black holes consume matter and emit radiation. The very structure of the universe itself, held together by a delicate balance of forces, could be different. The interactions between galaxies, stars, and other cosmic entities might be fundamentally altered. A massive photon could alter the expansion rate of the universe, the formation of galaxies, and the overall dynamics of cosmic evolution. And even the nature of dark matter and dark energy, those mysterious entities that make up the majority of the universe. These components are crucial to our understanding of the cosmos. The mysteries of dark matter and dark energy could be unraveled in new ways, offering insights into the fundamental nature of reality itself. The idea of a massive photon isn't just about equations and scientific theories. It forces us to confront profound philosophical questions about the nature of reality itself. If something as fundamental as the mass of a photon can be questioned, what else do we take for granted? What other seemingly unshakable pillars of our understanding might be built on shaky ground? This is the beauty and the terror of scientific inquiry. It has the power to upend our worldview, to reveal a reality stranger and more wonderful than we ever imagined. It's a humbling reminder that we are still exploring the shores of the cosmic ocean, and the greatest discoveries may still lie ahead. The possibility of a massive photon is a stark reminder that the universe is full of surprises. It challenges us to question our assumptions, to push the boundaries of knowledge, and to embrace the unknown. Perhaps the most mind-blowing aspect of this idea is that the answer could be right in front of us. We might be just one scientific breakthrough away from discovering that our understanding of light, gravity, and the very fabric of reality is incomplete. So, the next time you look up at the night sky, remember the humble photon. This tiny particle, this messenger of light, might hold the key to unlocking some of the universe's biggest secrets.